Good afternoon. Today we'll start to talk about one of the instrumentation. I will send you a video about this instrument, okay, in order to imagine the parts of this instrument and to follow me when I speak about each part of it. So shortly I will send you a video, and the topic is about gas chromatography. So the video will show you one of the instruments. We have them in the faculty. We have one of the advanced instruments of gas chromatography that GC. We have a abbreviation for gas chromatography instrument, which is GC. So we have GC with mass, and we have other kind of GC. But the GC with mass spectroscopy, we will discuss mass spectroscopy later on. This is one of the most expensive instruments, and it costs more than sometimes more than $200,000. So the main anatomy of any gas chromatography is porter, injector, okay. We have injector, and we introduce the sample here by syringe, and we can also see in the video that we have a robot. That robot can take the sample, and we have a rack in order to hold these samples. The robot will take regularly a sample from each unknown in order to introduce exact amount of it in GC instrument. Then we have injector, and injector is heated injector, okay. And then we have capillary column, which contains the stationary phase. Then we have detector. We have capillary column here. We have other kinds of columns, but this is the most popular column. And also we have what? We have something to might be considered as mobile phase, or people prefer to consider it as a carrier. This carrier gas, which is usually either nitrogen or helium, which act as mobile phase. Okay, so we introduce the sample by syringe. Okay, now we have to choose the compounds which are volatile in order to be tested by gas chromatography. Now, which kind of compounds are volatile? The compounds which is considered lipophilic and which has low molecular weight. So a huge compound like this compound, big compounds such as proteins and other kind of compound cannot be tested by gas chromatography because they have large molecular weight. The second thing, that the compounds which are hydrophilic, such as sugars, also without modification, they cannot be tested by gas chromatography due to their polarity. When the compound is polar, okay, consider this as a polar compound. Polar compound can make strong intermolecular bonds. So we will have bonds, okay, among the molecules from the same type of the analyte, this will adhere the compound among its colleagues, and in this case, the volatility of the compound will be negligible. And one of the good examples of such compounds is water or sugars. Okay, whereas lipophilic compound, which cannot form intermolecular hydrogen bonding or weak intermolecular bonds, then each compound will be free. So it can, if the compound takes the sufficient energy of evaporation, then it can be volatile. Okay, so generally speaking, that lipophilic compound with low molecular weight are volatile compounds, and these are the most suitable compounds for gas chromatography. Again, if we have lipophilic compound, okay, in ionized form, this compound cannot be analyzed by gas chromatography unless I remove the charge. For example, if we have alkaloid, okay, now we know that alkaloids are basic compounds. Okay, so if the alkaloid prepared as a salt by using, for example, if you precipitate alkaloid from organic solvent by adding acid, the precipitation is due to formation of salt. Salt is not soluble in organic solvent, so we will have precipitation for alkaloid. If you dissolve alkaloid in semipolar solvent and you introduce it in GC, the problem that alkaloid will be in salt formation. In salt form, the compound cannot be volatile, and this is due to ionic interaction. Ionic interaction is strong interaction. For example, sodium chloride cannot be melted in temperature below 800 degrees. Just melting, not boiling. Okay, so boiling, you need very high temperature. So you can deduce easily that ionic bonds are strong bonds, and salts cannot be melted in low temperature. You may see that we can simply dissolve sodium chloride in water. Why it is very difficult to separate sodium from chloride in neat form? Neat means without solvent. Yeah, sodium chloride bond is ionic bond, very strong, but water can separate them due to the dielectric constant of water. Dielectric constant of water near 70, maybe 78 or 73, I don't remember exactly, but it is around 70. So 70, that water is quite strong to remove two opposite charges from each other and to get each one separate from the other one. The molecule will be arranged around sodium ion and around the chloride ion in order to get them separated. That's why we put AQ. AQ means aqueous, that water will surround sodium ion. The same thing for chloride, will be surrounded by water ion. For example, the dielectric constant of ether is almost 0.5. Okay, so it cannot separate two opposite charges from each other. If we put sodium chloride in ether, it cannot be dissolved. Okay, and if we if we want to melt sodium chloride, okay, if you want to melt it, for example, to prepare sodium metal by applying the redox reaction, okay, to gain electron from electricity in order to form sodium, you need to melt sodium chloride, and this step need what? Need very high temperature. Okay. So you cannot use gas chromatography for ionized alkaloids, but if you add, if you have, for example, atropine hydrochloride salt, okay, atropine hydrochloride salt, if you add base like sodium hydroxide, it will take the acid portion of the salt, okay, the proton of atropine, and in this case atropine will be what? Will be again base unionized, oily soluble. And in this case we can, after treating atropine with basic compound, okay, then you can get it lipophilic, and consequently we can analyze atropine by GC, particularly when we have mixtures of alkaloids. In order to get them separated, I can use gas chromatography, but you have to have them in unionized form. Okay. This is about the type of the molecule which can be separated by gas chromatography. Another issue, that the quantity of material should be as less as possible. So usually we inject just 1 microliter. Okay? 1 microliter is sufficient. Okay? We inject 1 microliter from solution because we not only have analyzed, but also we have what? We have solvent molecules. So 1 microliter from solution can give all the system in GC is heated to keep the molecules in what? In vapor phase. So once we inject sample, the injector will be at high temperature in order to keep or to make the solution gaseous. So the solution will be gas here. So gas, we know that we will have volume expansion. 1 microliter will make significant volume expansion. So this is one of the reasons that we cannot increase the sample more than 3 microliter. More than 3 microliter, we will have very big volume for the sample, and this cannot be contained in the limited space of the injector. Okay. And even if we push the system to have more than 3 microliter of the solution, which should have large volume and gaseous phase. In this case, instead of having a flow from the carrier gas to this direction, the excessive pressure of the gas inside the injector will oblige the system or the flow of the nitrogen or helium to go backward, and we call this backflash. This backflash, that instead of having the sample into the stationary phase, it will go to the carrier gas. We will lose part of the sample. Okay, and this is very bad. It has very bad consequences on the separation. So you have to make the injection as least as possible by introducing just 1 to 3, maximum to 3 microliter. And you know that the solvent molecules are abundant molecules, and they contribute significantly in the pressure inside the injector. So in order, as we said, in order to reduce the chance of backflash, we have to reduce the quantity of the injected sample. Okay. Now, 1 microliter is very minute quantity of material. How can we inject 1 microliter? Practically, we cannot. We might inject 1.1 microliter or zero point 0.9 microliter, or if we are not expertise, we might inject 1.5 microliter or something below 0.6 microliter. So you cannot guarantee that you inject exactly 1 microliter, okay? Because it is very minute quantity. Now, in order to overcome the problem, we have to add something we call it internal standard. Internal standard. Okay. What do we mean of internal standard? Now, in order to understand what do we mean of internal standard, we will take a case. And from this case, we might be able to conclude the meaning, the real meaning of internal standard. Now, assume that we need to quantify the content of carbon. Carbon, one of the volatile oils in one of the plants. And we have standard of carbon. So we have a plant which might contain certain quantity of carbon. We don't know exactly how much carbon do we have in the sample. And we have carbon as a standard material. We call carbon as standard material external standard. External standard because we can put it in a separate container, separate flask. So we will prepare 2 flasks. One of the flasks contains the plant which is expected to have carbon. The other sample which contains the external standard in separate flask contains certain quantity of carbon. For example, 1% volume per volume of carbon. So we put, for example, 1 mil carbon to 100 mil solvent like methanol, like ethanol, like hexane, any solvent suitable, any organic solvent or semi-polar solvent, in order to be volatile. I cannot dissolve in water. Okay. Look. So we inject carbon or the plant extract firstly, as you wish. So once we put 1 microliter of carbon, in order to quantify the quantity of carbon in the plant extract, I inject 1 micro, but it is not necessary to be exactly 1 micro. So if I inject, for example, by error 2 micro instead of 1 micro, then I will have a duplicate quantity of carbon in the plant extract. And this is scientifically not acceptable. So how can I remove the error of the volume during the injection on the final results? The idea that you can use internal standard. Internal standard, I will add another compound which can be easily separated from carbon by GC, and I know the quantity of it in each container. For example, I put thymol. So I put here 1% thymol. That I add 1 mil of thymol to the flask, and I will make the volume to 100. So the quantity of thymol in the sample here will be 1%. The same thing, I will put exactly the same amount of thymol in standard. So I will put also 1% of thymol in standard container. So the same quantity will be for internal standard in both thymol and extract flask and also and standard external standard flask. Now, if we have any error in the injection, it will be reflected on the thymol peak. Thymol will be separated from carbon. If we inject the same quantity, 1 micro from standard and test, thymol will give rise the same area under the curve, the same response in two chromatograms, the chromatogram of the standard and the chromatogram of the test. If we have error, then this will be reflected on the internal standard. And mathematically, we can make adjustment of the calculation according to the thymol quantity. Okay? In order to understand this, what do we mean exactly? I will give you a suggested chromatogram for this case. For example, the standard, which is standard, carbon standard, give two peaks. Okay? One of them for carbon, the other one, let's say I don't know which one is for carbon and which one for thymol. Okay? Then plant, this is for example 5 minutes retention, this is 10 minutes retention. Okay? The plant give us peak here, okay, and peak here and other peaks. Okay? Again we have peak at 5 minutes and peak at 10 minutes. If you don't know which one is carbon and which one is thymol, you can inject sample just for qualification, as a qualification test, not for quantification. You just inject thymol alone or carbon alone. For example, I inject carbon alone just to see the retention time, and I found that the retention time is 5 minutes. So I know now this is carbon, this is thymol. In the plant extract, of course, 5 minutes, the same 5 minutes will be carbon, and the one will be thymol at 10 minutes. Now, the computer of the instrument will give me area under the curve, or both the tested compound and the internal standard. Now, if we have area under the curve similar in the two injection, the injection of the standard and the injection of the plant extract, then the volume will be similar. Okay, the volume of injection will be similar, and any deviation of the area under the curve for the carbon will directly reflect the real difference between the sample and the standard. Here, if the area under the curve 100,000 and the thymol in the plant extract 100,000, then there is no difference in the injection volume. So, if the standard, as I said, that the concentration of it 1%, okay, and we have area under the curve 50,000, okay. Now in the plant extract we have it 100,000. So in the plant extract the area under the curve is twice the area under the curve of the standard. Okay, the standard has a concentration of 1%, so the concentration of the carbon in the plant extract will be 2%, because the area under the curve is duplicate the area under the curve of carbon in standard container. Okay. So now we can see easily that the concentration of the carbon in the plant extract will be 2%. Okay. Let's take another scenario. In the standard material, we assume that thymol is 50,000 when the plant extract is 100,000 for thymol. So the concentration of thymol in the plant extract is duplicate that in standard container. Thymol, I put the same quantity. So the duplicate of the quantity is due to what? Duplication of volume, because the concentration should be similar. So instead of, I will assume anything I want, just duplicate. Instead of inject, for example, 1 micro, I inject in the plant extract 2 micro. Or instead of 2 micro, I inject 4 micro. I duplicate the quantity in the plant extract comparing with the standard container. So this should reflect or affect. This should affect the calculation of carbon directly. If the carbon in standard give me 50%, okay, and the plant extract give me again 100,000. Now, what is the quantity of carbon in the plant extract? Okay. So, from thymol, we said that we duplicate the volume. Instead of 1 micro, we inject 2 micro. Okay. So 100,000 area under the curve for carbon for 2 microliter. But if we have 1 micrometer, what is the area under the curve? It will be half 100,000. It will be 50,000. So the corrected area is 50,000. Corrected according to the volume. Now, what is the quantity of carbon in the sample? Area of the carbon in the sample, the same area of the carbon in the standard. The concentration of carbon in the standard is 1%. So the concentration of carbon in the sample is again 1%.